Oftentimes, when we are trying to explain something to a friend, we use an expression that is similar to the one that we're trying to convey. Usually, that makes it easier for our friend to understand what it is we're trying to convey. This is true in mathematics as well. Hi, my name is Tom Atwater, and we're going to be working with trigonometric identities in today's lesson. Let me start by defining an identity. An identity is an equation which is true for all values of the variable for which both sides of the equation are defined. The set of all such values is called the domain of validity of the identity. Let's take a look at the basic trigonometric identities. Let's start with the quotient identities. The tangent of theta is going to be equal to sine theta over cosine theta, and the cotangent of theta is equal to cosine divided by sine. The reciprocal identities. Cosecant theta is equal to 1 over sine theta. Secant theta is equal to 1 over cosine theta. Sine theta is equal to 1 over cosecant theta. Cosine theta is equal to 1 over secant theta. And tangent theta is equal to 1 over cotangent theta. And cotangent theta is equal to 1 over tangent theta. Well, there are some more identities that I want to show you, and they're called the Pythagorean identities. And they work like this. Cosine squared of theta plus sine squared of theta is equal to 1. 1 plus tangent squared theta is equal to secant squared theta. And cotangent squared theta plus 1 is equal to cosecant squared theta. Let's work an example where we use these identities. I want to find the sine of theta and the cosine of theta if the tangent of theta is 3/4 and the sine of theta is positive, without using a calculator, but using the Pythagorean identities. So, what I want to first say is that if the sine of theta is positive, and of course tangent theta is positive, that means we're dealing with angles that are in the first quadrant, or an angle that's in the first quadrant, I should say. Therefore, we know that the sine theta and cosine theta that we're looking for will be positive answers. All right, so let's work with it now. What we know from the Pythagorean identities is that 1 plus tangent squared theta equals secant squared theta. And in this case, we know that the tangent of theta is 3/4. So we have 1 plus 3/4 squared equals secant squared of theta. Now, 3/4 squared is 9/16. And we rewrite 1 as 16/16. So we have 16 plus 9 for 25/16. And that equals secant squared theta. We take the square root of both sides. And normally when you take the square root, you say, okay, it's plus or minus the square root of 25/16. But we can say that we know that the angle is in the first quadrant where all of the values are positive, so we don't need to take the negative square root answer. So this is just the square root of 25/16, which when we simplify is 5/4. So the secant of theta is 5/4. Now we can find secant, remember, is 1 over cosine, which means the cosine is simply the reciprocal of this secant. So let me erase this and write down that the cosine of theta is 4/5. That is, it's the reciprocal of the secant that we just calculated. Using the Pythagorean identities again, I can say that cosine squared theta plus sine squared theta is equal to 1. But we know that the cosine theta is 4/5. We have to square that, which makes it 16/25, right? And then we have plus sine squared theta equals 1. We need to subtract the 16/25 from the left-hand side of 1, and we need, therefore, to change the 1 into 25 over 25. that'll give me sine squared theta is equal to 25 minus 16, or in other words, 9/25. Take the square root of both sides. We're only interested in the positive value because this is in quadrant 1. So we know that the sine theta is the square root of 9/25, which is 3/5. So using those identities allowed us to find both the cosine right here and the sine without using a calculator. Now we're going to define the cofunction trigonometric identities. And the cofunction trig identities are this: that the sine of pi over 2 minus theta is equal to the cosine of theta. That the cosine of pi over 2 minus theta is equal to sine theta, and the tangent of pi over 2 minus theta is equal to cotangent theta. Then we also have the next set, which is the cotangent of pi over 2 minus theta is equal to tangent theta. We have the secant of pi over 2 minus theta is equal to cosecant theta. And then we have cosecant of pi over 2 minus theta is equal to secant of theta. Let's work an example of where we use the cofunction identities. We want to find the sine of theta. We have the sine of theta is equal to 45/100ths, and we want to find the cosine of pi over 2 minus theta. Well, from our identities, the cosine of pi over 2 minus theta is equal to the sine of theta. And we were given that the sine of theta is 0.45, so that means that's our answer for the cosine of pi over 2 minus theta. It's 45/100ths. So now what I want to do is look at the odd identities. And the odd identities refer to the fact that these are odd functions. And if you remember from functions, if we take f of negative x, that's equal to negative f of x. And that's what you can see for these odd identities. And those are sine, its reciprocal cosecant, tangent, and its reciprocal cotangent. Now we'll take a look at the even identities, which of course would be the only two remaining, cosine and secant. And you remember with even functions, the f of negative x is equal to f of positive x. And that's what we see in operation here. The cosine of negative x is equal to the cosine of positive x. Now, let's work an example where we combine some of these identities together. Let's say if the sine of theta minus pi over 2 is equal to 73/100ths, then find the cosine of negative theta. Okay, so let's start by working with this part of the problem. And notice that I can rewrite the sine theta minus pi over 2 as the sine of negative pi over 2 minus theta. And I do that because now I can use the odd identity that the sine of negative x is equal to negative the sine of x. So this is equal to negative the sine of pi over 2 minus theta. All right, now that's helpful in that I can now say up above that if I take this we know is equal to 0.73. So now what I can do is say that the sine of pi over 2 minus theta is equal to negative 0.73. The reason that's helpful is, what do I know that the sine of pi over 2 minus theta is equal to in terms of the cofunctions? I know that this equals cosine theta. All right, well, that's helpful because I'm getting closer to this answer here. But in terms of the even function identities, cosine of negative theta is equal to what? Cosine of positive theta. So therefore, the cosine of negative theta is the same as the cosine of positive theta, which means if I follow this loop back around like this, cosine negative theta equals cosine theta, which equals the sine of pi over 2 minus theta, which equals negative 0.73, I can say that the cosine of negative theta is negative 0.73. All right, so that's an example where we used 3 different identities in order to solve the problem. Now, as I said at the beginning, we often use identities along with algebraic techniques to simplify trigonometric expressions. Let's work some examples of where we'll do that. We want to simplify the expression quantity secant x plus 1 times quantity secant x minus 1, all divided by sine squared x. And what I'm going to do is simplify the top of this first. Notice that we just simply expand through the distributive property. And I want you to notice that's just the difference of 2 squares. So therefore, this is equal to secant squared x minus 1 on the top. And the bottom remains sine squared of x. Now, secant squared x minus 1, that should be familiar because, yes, we have that 1 plus tangent squared equals secant squared. And what that means is that the tangent squared would be equal to secant squared minus 1. Ah, voila. We can make that substitution. Oops, sine squared x. What do we know tangent is equal to? Tan x is equal to sine x over cosine x. So therefore, tangent squared x would be equal to sine squared x over cosine squared x. And that's all still over sine squared of x. But now my sine squareds can cancel to 1, right? So that this entire expression becomes 1 over cosine squared x, which we can go one step further and say that that is equal to secant squared of x. So this entire expression here all simplifies to secant squared of x. That was the algebraic way of looking at it. Now, I just want to support this graphically. So what I'm about to show you is plugging into the grapher the original expression as y equals that, and then also entering into the grapher y equals secant squared x. Now, if in fact they're equal, what should happen on the graphs? Well, what should happen on the graphs is that they should overlap each other. That is to say, they should appear to be the same exact graph, and that's exactly what I was able to find when I plugged it into the grapher. Okay, now we're going to explore solving trigonometric equations. Find all the solutions to the trigonometric equation 2 sine squared x plus sine x is equal to 1. So, first thing I want you to notice is that's a quadratic equation. It's a sine squared. So we're going to look to see if we can factor this. But the way to do that is first I need to rewrite it as 2 sine squared x plus the sine of x minus 1 equals 0. And now I want to see if I can factor it. If it's going to factor, it's going to factor as 2 sine of x and sine of x, and that's going to have to be a 1. That's going to have to be a 1, and of course it's still equal to 0. And now it's just a question of, ooh, does this work out? It sure does. If I put my minus sign in the first one and my plus in the second, then I would notice the middle terms would add up to positive sine x. So what I get is that the sine of x is equal to positive 1/2, and I get that the sine of x is equal to negative 1. All righty. Well, the sine of x equaling 1/2, that is one of the angles that you should memorize, pi over 6. But also, we weren't given any restrictions, which means we also have to think about where else is sign positive, and that is in quadrant 2. So the angle in quadrant 2 is 5 pi over 6. However, further than that, we also have to remember that it's periodic, so that this would be pi over 6 plus 2 pi times n, which then takes all of the periods into account, or takes the period into account for all of the angles that would be work for that. We would also have 5 pi over 6 plus 2 pi n. All right, what about sine x equals -1? All right, that falls on one of the axes, doesn't it? In fact, that works out to be the equivalent of 3 pi over 2. But again, we have to take into account all of the period for that and all of those angles. So I would have 3 pi over 2 plus 2 pi n. And that would give me all of the solutions to that original trigonometric equation. Now it's time for you to try a problem. I want you to find all the solutions to the trigonometric equation 4 cosine squared x minus 4 cosine x plus 1 equals 0 in the interval 0, 2 pi, which means you're only going to be finding answers that are in that interval, not the multiples, as in the example I showed you. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Let's see how you did on this. This is the original problem. Let me create a little bit more space for myself, and let's look to factor this. What I hope you noticed is that this factors as a perfect square. 2 cosine x minus 1 quantity squared equals 0. And therefore, 2 cosine x minus 1 equals 0. And therefore, cosine x equals 1/2. So now you know that you have to find that angle, but again, that's one in which you should have memorized, and therefore x is equal to pi over 3. However, we're in the interval from 0 to 2 pi, so the question is, where is cosine of x positive? Quadrants 1 and quadrant 4. Therefore, it's pi over 3 in quadrant 1, and it's 5 pi over 3 in quadrant 4. So those are the two answers that you should have gotten when you solved that trigonometric equation. All right, great work in today's lesson. So in this lesson, we explored trigonometric identities, and we applied that to simplifying trig expressions, as well as finding and solving the solutions to trigonometric equations. Be sure to work the exercises that your teacher assigns, and we'll see you next time.